So, hello everyone and welcome. Today we're going to have a talk by Lars Andersson, who is a mathematician, but with quite a lot of work in physics, general relativity, and also cosmology. So I invited him to talk today about some of his work, and he's going to talk about cosmological models and stability. As far as I understood from the abstract, he's going to talk about the different principles that we have in cosmology that, let's say, we as physicists usually tend just to assume, but mathematicians want to be more rigorous. So he's going to discuss about this. And Lars, feel free to start whenever you want.
Okay, yeah. So thanks for the invitation. Yeah, so I should say this is an old talk that I haven't really updated. And it was, it was given, I gave this first time at a conference in Prague. Then I thought, Einstein spent 1 year in Prague, and that's where he sort of came up with the equivalence principle, or at least one version of that. And so I wanted to talk about principles in cosmology and basically state some of my views on this. And on the topics of the talk, there has been quite a lot of developments. Over the last 10 years, in particular, issues of, inhomogeneities in cosmology haven't gone away. And there's also been a lot of mathematical work on various issues of stability and so on. So maybe it's so the topics of the talk may be worth coming back to, I think. Let's see here. Yeah, so I started with this quote by Kepler, and what it says is that I would already have concluded my research about world harmony had not Tycho's astronomy so shackled me that I nearly went out of my mind. So this was the tension between pure principle, which was the harmony of the spheres and all that that Kepler was inspired by, but the actual observations coming from Tycho Brahe, around the same time, that caused a lot of headaches, and that was what eventually led to Newton's work, I would say, and the idea that you have motion on ellipses and so on, Keplerian motion. So I think that's kind of funny quote. So I think, I just included this for the sake of it. So of course we're talking about the Einstein equations, and as if you contrast that to Newtonian physics, there is no action at the distance. You have instead test particles moving along geodesics. And the matter content is described by the energy momentum tensor. Okay. And the principles that were behind this were the special relativity, so Lorentz covariance, coming from late 19th century, and the Machian ideas, which were led to the equivalence principle. And this is what I was emphasizing this year when the year that Einstein spent in Prague, 1912. And there's the principle of general covariance, but there were also some significant observational anomalies that were known at that time. and in particular the precession of the perihelion of Mercury. So, I mean, all of this is, of course, extremely well known. And this had been known since around 1860. So it took quite a while for this to work out. And of course, there's also behind this, there is the tension between, Lorentz invariance or covariance coming from Maxwell theory, and the fact that that is not compatible with Newtonian physics. And this led to the whole ether theory that was another kind of sidetrack in the 19th century. And once it was accepted that the GR could explain the precession of the perihelion, and also the fact that you get the correct deflection of light, which was observed in connection with this eclipse 2000, I think it was 1916, something like that. Then this GR on this very kind of flimsy grounds was very quickly accepted. And of course, if you have a good theory, you want to apply it to everything. I just also, I think it's a kind of funny fact that people should really think about, is that attempts both to explain this precession of the perihelion of Mercury had been made in the 19th century, both in terms of dark matter, so some matter that was not visible, and this was given the name of the planet Vulcan hypothesis. And also people were, also in the 19th century, modified gravity was being tried. So modifications, for example, to the inverse square law. And of course, none of that worked. And eventually general relativity came along. But I think one should not forget that the various modifications of general relativity that people are talking about today have their counterparts in the 19th century. And so I think that's a kind of, there is a moral to that story. And on the other hand, so there are other well-known problems of Newtonian cosmology. Olbers paradox basically saying that why is the sky dark? And there are also serious problems when trying to understand infinitely extended self-gravitating Newtonian systems, which you would, in Newtonian cosmology, that's the natural thing, so to speak. And so there are some serious problems with trying to apply Newtonian principles to cosmology. So that's another reason why Newtonian physics had to go by the wayside. So Einstein already in 1917 proposed this Einstein universe, the static cosmological model, and that introduced the cosmological constant, which we are still struggling with today, so to speak. And as well, so as you all know, so Friedman introduced this model for the expanding universe, and that plays a remarkably important role in modern thinking about cosmology. this very, very simple-minded sort of ansatz. This has the side effect that it can solve Olber's paradox if you have an expanding relativistic model like this. Well, so here I mean, I think all of you know, everyone knows this, but I'm still repeating this. So there was, so Hubble's law was introduced based on certain observations relating distance to redshift using the certain pulsating these stars with certain varying light, varying magnitude, and then they came up with this, and relating that to redshift, they came up with this fitted curve, which has not extremely good fit, so to speak. And there are other, so trying to develop a cosmological model, you can try to impose various principles, and ideally, these will be eventually laying a foundation for using the Friedman model. One of those is that there are no special observers. We are not special in the universe, so to speak. A stronger form of this principle is what's called a cosmological principle, saying that the universe is isotropic, and then some geometry. So this isotropic means that there is no special direction, and this leads to saying that by some geometry leads to saying that the line element in cosmology is a Friedman line element. So this was known in the 1930s. And then there's the even stronger cosmological principle, which is today mostly forgotten, but there's the perfect cosmological principle. And this was introduced by Bondi, Gold, and Hoyle. And that says that the universe is isotropic in space and time. So there's no special place, and there's no special time. And this is so these guys were atheists, and of course Lemaitre was a Jesuit priest. So there's already a tension there, that there in standard model cosmology there's a moment of creation, but Bondi, Gold, and Hoyle wanted to do away with this, so they had this perfect cosmological principle, and that leads to certain problems which required certain ad hoc assumptions, and at the time this was viewed as not tenable. So that principle is not really discussed anymore. I think it's still something to keep in mind. It's not crazier than anything else. Okay, so if we talk about the Friedman model, then we can talk about the matter content, and you can think of so the matter must be a fluid, so you can think of a collection of fluids, and for example dust, the curvature, and the cosmological constant can be treated on the same footing. By some simple considerations from the properties of the fluid, you can get the scale dependence of the densities. And so here A is the scale factor in the Friedman model. You can then use these dimensionless numbers as parameters for the cosmological model. And the Hamiltonian constraint coming from the Einstein equations says that the sum of these parameters has to be 1. And you can sort of recast the Einstein equation in terms of these parameters in this way, where h here is the Hubble constant, so a dot over a. So that's a function of time that describes the rate of expansion of the universe. And you can then, you can integrate this to relate it to cosmological, to observable quantities, starting with some parameters, h naught, omega and the omega naughts. And so now you can compare this model to observations. And so what we're looking at is, so this basically is some important component of the standard model in cosmology, and that is valid. That's true also today, and is, well, to some extent being challenged by observations, but has not been abandoned. And so here's a simple comparison between the supernova data and these simple models. So what we have here is Milne, which is the flat empty universe with curvature -1. The black one is the standard model with those parameters set to certain values, which I mentioned. And the green dashed curve is Eddington, Einstein de Sitter, which has spatially flat, but has a critical amount of dust matter. And so if you compare this data to, I think this is to the Milne, then you see that there's quite a bit of scatter. The standard model, well, fits okay. The Einstein de Sitter does not fit well. But if you, depending on your opinion, you can say that, well, there's a certain difference between the standard model and the flat empty universe, but it's not at least from this very crude analysis, is not a very great difference. Okay, so as I said, we have the laws of general relativity, we have the cosmological principle, which leads to the Friedman model, observations, and plus the assumption that we have these different types of fluids. Then you can say that, well, it looks like the universe can be approximated by a Friedman model with a positive lambda, and which is spatially flat and has about 30% of matter content. And some of this, I should emphasize, based on other considerations, most of this matter which is in this model is not visible. It's not, you can't relate it to visible matter. And you can also argue that most of this 30% of matter is actually non-baryonic. So it's some kind of exotic type of matter that we cannot know. And this is the dark matter that's still being looked for. And this, I mean, there are indications that there's dark matter in from all sorts of observations, from all sorts of dynamical observations. And so, I mean, Fritz Zwicky introduced this notion based on studies of the dynamics of galaxy clusters and so on. So this has also been around for a long time. And it's a Big Bang model. It predicts a hot Big Bang and so on, and the cosmic background radiation. And this was, predicted quite early, even though they had because the value of the Hubble constant at that time was quite wrong. So they had the temperature was quite off in their calculations. Okay, and but the point I'm making, or the one point I think is important, is that homogeneity and isotropy hold at best approximately. So in fact, the universe is not exactly homogeneous and isotropic. So here are some old, here are some old pictures of cosmological surveys which indicate that there's a certain amount of inhomogeneity. And also, if you look at the CMB, the cosmic microwave background, that is also not perfectly homogeneous. So there are variations here on the order of 10 to the -5 and so on. And of course, one has to understand what are the consequences of these inhomogeneities. So there are certainly inhomogeneities in space, so to speak. And there are certainly non-isotropies. And furthermore, if you look at so I wanted to list here some problems with the cosmological models that I think are still around and which one should not forget about, so to speak. So one of those is the horizon problem. I mean, why is the universe homogeneous? Because if you take the Big Bang seriously, you can you can argue that unless there's some special thing going on at the Big Bang, different parts of the universe haven't had time to communicate, so to speak. And therefore, there is no explanation why the universe is homogeneous. And so the standard explanation for that is inflation. And, it's everyone's choice whether to take that seriously or not. I think it's there are many problems with inflation. There's the flatness problem. So why is the spatial curvature nearly very, very close to zero? So there is some kind of fine-tuning going on. And both of these problems are essentially supposed to be solved by inflation, but I think that's not a solution that's a solution that introduces many other problems, let's say. So I think those issues should still be taken seriously. And there's also in the standard model, there's the why now problem. I mean, because we're living at a time when according to the standard model, the density of corresponding to the cosmological constant and the density of the matter is they're roughly proportional. So they're too close. You would not expect them to be that close unless there's some deeper explanation for that fact. And so if you plot this in time, you see that in the early time, so at present, so the density of the cosmological constant tends to dominate at late times, and we're now at which would mean that it tends to 1 at late time. So we're now at some intermediate place, but due to the way things scale, this on a cosmological time scale, this is a very short amount of time. So there's some explaining to do why it happens that these two densities are nearly proportional or nearly equal, let's say. And so these are problems that I think do need to be addressed, and I'm sure many people in cosmology are thinking about this, but I think it still one needs to have some. It needs to be brought up time and again. And basically as saying that there's the standard model from this point of view is perhaps incomplete in some sense, because what this says is that we're living at a very special time in the universe, even though we're not supposed to be special observers, so to speak. And one could come up with some anthropic explanation for this, that this is the only time in the universe where there can be intelligent life and so on. But, well, that's another discussion. So here's a quote which sort of puts this into focus. What they said, so these are, Plebanski and Krasinski, those are, they wrote a book on relativity, and Krasinski has also written about inhomogeneous cosmological models. So the fact that virtually the whole of observational cosmology is based on the Friedmann-Lemaître model is a consequence of inertia in thinking and emotional attachment to the mathematically elegant and appealing doctrine of exact equivalence of all positions in the universe. So one can agree or disagree with that. But so you can ask yourself, is it possible to replace the cosmological principle by something that is more likely to be valid, statistical homogeneity, and you can also talk about matter bound, or because we are living in an overdense region, so that introduces a certain bias, and I think that can be used to argue about these things. And so these inhomogeneities lead to many problems. So in particular, so one thing is, what are the dynamical consequences of inhomogeneities in cosmology? People have talked about fitting problem and averaging and so on. And the nature of the matter distribution and the effects of inhomogeneities on observations. Inhomogeneities will affect the propagation of light in the universe and so on. So all of these things are potential issues and should be kept in mind, so to speak. But there are also mathematical problems that are raised by this, which have had. So there's been quite a lot of attention to this in recent years. So the Ehlers, Geer, and Sachs theorem is a theorem that says that, or quote unquote theorem that says that if the cosmic microwave background, the CMB, is perfectly homogeneous, then the universe has to be homogeneous. So this is actually this is true only with some strong additional assumptions. So there are counterexamples to that, to the statement I just made. You also have, problems of stability and instability. A good model in physics should be stable in some sense. Therefore you can ask yourself, is the Friedman model stable? And if it's not stable, how can that be analyzed? And it's also interesting to think about the asymptotics at the singularity and in the expanding direction. So for example, so what we're from a certain point of view in the late universe, but of course one could expect time to go on forever. So what's the asymptotic state in the expanding direction? So you can do some kind of simple-minded or simple dynamical systems analysis. So as I said, if you think about the three, you have these three densities, which are time varying, dimensionless numbers, and you can then use the Friedman model, the Einstein equation, to write down a dynamical system for these models, and you can analyze that dynamical system. So that's been done in great detail. And as I mentioned earlier, if lambda is positive, then the lambda density will dominate as time goes as you go to future infinity. And if we restrict to lambda 0, then you can describe the phase space as in this picture. So there's a fixed point corresponding to Einstein de Sitter, and which has the critical matter density, and that fixed point is unstable. And in one direction there is the miln, which is the empty flat universe, which has omega curvature equal to minus omega curvature is 1, but the curvature is -1. And then in the other direction, you have basically models that collapse to the future, so big crunch. So the message here is that unless you have lambda, then the empty parts of the universe tend to dominate. and also I emphasize that the action de Sitter is unstable. So you can apply this kind of reasoning also locally. So this kind of instability is what causes the over and under densities in the universe, you could naively say. And this Milne model, which is basically the empty universe, is stable within the Friedman models, and that has rapid volume growth, whereas the action de Sitter has this kind of slow volume growth, t to the 2/3. Okay, and so because it's so simple, the Milne model, it can be analyzed quite easily, but it's so here's a picture of the Milne universe. So it's simply the flat interior of the light cone in Minkowski space, and the cosmological time slices are these hyperboloids. And as you go towards the past, you approach a Big Bang, but the Big Bang in this case is just it's just the boundary of the light cone. So it's a perfectly smooth hypersurface. And the universe in this case can be extended past the Big Bang. But you can make this this model inhomogeneous, so for example, so one way to do that is this is still a flat model, but here the Milne model has been deformed by cutting it open along a plane, a hyperplane, and then gluing in another flat universe. So this spacetime is so here the Big Bang has this kind of interval. So here the Big Bang, you can say it's this point, but here the Big Bang, you have a different structure at the singularity, and this is not isometric to this Milne model. And important fact is that this deformed region has slow volume growth, but the undeformed region there you have for these particular slices, which would be sort of constant, you could say sort of constant Hubble, level sets of the Hubble constant, so to speak. There you have slow volume growth versus fast volume growth. Okay, so that's just one simple example, and this can be so there's quite a bit of mathematical analysis that has been done for flat cosmological models. And so here are some papers talking about that. You can have quite complicated structure at the singularity, at the Big Bang, so to speak. And you can analyze the future asymptotics of such models. And the typical picture is that if you look at, so this is supposed to be a sketch of a Cauchy surface in one of these models, and you can decompose this into sort of thin and thick regions, or neck regions and hyperbolic regions, where in these regions the geometry looks like hyperbolic space. And that's basically coming from the fact that you have these hyperboloids, which are each of these is a copy rescaled copy of hyperbolic space. So this, when you analyze these models, you realize you can decompose them into sort of neck regions and essentially hyperbolic regions. And the neck regions have slow volume growth. Hyperbolic regions behave like mills, so they have fast volume growth. And so people have tried to argue that the voids in the universe, being empty, tend to behave like locally like a mill universe, whereas overdense regions tend to behave, more in the, more have slower volume growth, and therefore there's a competition between these slowly expanding regions and the rapidly expanding regions. And so in a kind of statistical sense, at late time, you would expect the rapidly expanding regions to dominate. And this can be made rigorous in some simple cases. And so what this leads to is a typical sort of volume averaged observer actually lives in a thick region which has been expanding a lot. And various people have tried to argue or come up with analysis which is based on taking into account the fact that we are biased by being a matter-bound observer, and taking into account the dynamical role of these sort of empty regions which are rapidly expanding. Okay, so yeah, now this is becoming more and more mathematical, so to speak. So I'll go through this quickly. And so one approach to analyzing the global structure of a space-time is to think about the Einstein flow, which is basically the time evolution of the geometry on Cauchy slices. And it's one approach is to look at constant mean curvature Cauchy slices, and then you have the Hubble time comes up naturally, and you can look at scale-free geometries and look at the flow of these scale-free geometries in terms of this Hubble time. And so this is now a flow of geometry, so to speak. And in the 2+1 dimensional case, this can be completely analyzed. And what you find is that in that case, the two geometries, the spatial geometries, can be described as Riemann surfaces, and the space of these geometries is the Teichmüller space. And so a cosmology is then, you can think of that as a flow in Teichmüller space. And in the past, when you tend to the Big Bang, then you move to the boundary of Teichmüller space, which consists of degenerate Riemann surfaces, so to speak. And to the future, you settle down at a point in the interior of Teichmüller space. And so that corresponds to the fact that this rescale geometry converges to some asymptotic geometry. So this is the 2+1 case. So it's very, very restricted, but can be analyzed completely. If you try to think about the 3+1 dimensional cosmologies from this point of view. Even if you restrict to vacuum, this is very, very complicated. But you can come up with a general scenario that says that if you look to the future in this Hubble time, then the geometry will decompose into hyperbolic pieces and necks, so ciphered fibered pieces that are basically collapsing. And that sort of fits with this idea that I mentioned earlier, that over time, so here in this case, negative curvature, negative Yamamoto type goes together with vacuum or empty space, and this mathematical scenario fits with this naive sort of cosmological scenario that I mentioned earlier. And so here's a sketch sort of illustrating this, that over time, in the far future, what you will see are only these hyperbolic pieces. And so most of the volume, and if you sort of include matter, then what you would expect is that the most of the volume will be in empty space, and the matter will represent a smaller and smaller part of the volume. But you can also ask yourself about stability. So if you're close to a certain Friedman model, so if you say that, okay, so the universe is nearly Friedman, is that a stable statement? And so in the simplest case, one would like to prove that for Cauchy data close to Milne, so close to this empty cosmological model, then the future asymptotics is asymptotic to Milne. So this would be a stability statement. And so we were able to prove that in the vacuum case quite a number of years ago. You can then ask yourself a more general question. If you look at some Friedman models, are those stable in this sense? And so there's been quite a lot of work on that in the mathematical literature recently, well, over the last 10, 15 years. There have been many results coming out, which include different types of matter, including Vlasov. Okay, so I also mentioned here the stability of Minkowski space, which was the proof of that was a big breakthrough in sort of from the mathematical side. This led to quite a number of PDE people from the PDE community coming into general relativity, this has kind of changed the dynamics of the field, so to speak. And so I don't need to say much about that. You can also you can look at the dynamical consequences of having a positive lambda. So there, what you find is that things you can prove mathematically that the universe is essentially asymptotic to the sitter in a certain sense, and to the future. And this has been done with various types of matter around. Yeah, so Hans Ringström is one of those who has done a lot of work on this topic, and also Rodniansky and Gerrit Speck, and many people are working on that kind of thing now. Okay, and so let's see here. Yeah, so I think I'll just skip this, and so I just mentioned one more thing because I think time is running out.
Yes, you have 5 minutes.
Yeah, and so I just so I'll skip this. Let's see here. So I just want to come to one sort of cute result, which I haven't thought about for a long time, if you do this kind of dynamical systems analysis for certain kind of certain very simple kind of which are generalized Kastner models. So Kastner is one of the kind of standard cosmological models, and this generalized Kastner has basically two scalings, and it surprisingly turns out that that Friedman is stable within these kind of slightly more general. So this is this generalized Kastner is a generalization of Friedman with two scale factors. Friedman is stable if the space-time dimension is high enough. And it happens to be that the 11-dimensional case, which is kind of popular in supergravity, is the marginal case. And what these pictures show is the kind of phase portrait of this dynamical model, of the dynamical system that governs this model. And so here you have like an expansion point, and here you have this kind of swirling behavior that signals instability. So this is just I just want to end by mentioning this kind of cute result. And so there's also, as usual, there's been quite a number of papers on this, but this was done. Mark Hinault and others looked at this kind of thing, and I also did this with one of my postdocs. And so you can, so what I want to end with is that you can actually use these results to construct smooth full parameter families of smooth cosmological solutions, or actually real analytic cosmological solutions that have all these nice properties. So there's a global time function. There's a Big Bang where that has all these, it's a quiescent and crushing. It's future causally complete, asymptotic to Friedman to the future, and so on and so forth. So this is kind of a cute mathematical result that was motivated by thinking about the cosmological problems. Okay, so so I think I'll just end there. Thank you.
Thank you very much, Lars. And do we have any questions for Lars? If yes, feel free to just speak. If no one wants to start, I actually have a question You mentioned is that we could be basically biased towards certain interpretation of the cosmology, let's say, because we are matter bound, right?
Mhm.
Is there some, like, can you think of some observational evidence that we could find to realize that we are biased, or are we doomed to still to stay agnostic about finding this out from an experimental point of view?
Well, I mean, it depends on what you mean by biased. I mean, so I mean, someone who has has thought a lot about this is David Wiltshire, and so he tried to incorporate this kind of that there this kind of that you have these uh, so he tried to formalize the matter biased observer, and he tried to use that to describe sort of back reaction and so on. And so he's come up with some kind of, so this leads to some kind of basically modification of Friedman that he claims to be better fitting than the standard model. I can't really, but and that that can basically reduce the role of the, because what we see or what is being observed is this tension between a matter-dominated cosmological model with slow expansion and the observations that indicate that there's this what is interpreted as accelerated expansion, right?
Yes.
But as I indicated in some slides early on, if you compare the standard model, which has matter and cosmological constant, to a purely empty universe, at least if you squint, it doesn't seem to be that different, right? So the necessary additional expansion that you need to fit cosmological data, for example, supernova data, is not that great. And so what David Wiltshire, I think his point is that you can lessen the need, let's say, for having a cosmological constant by taking better into account the matter bias of observers and the fact that voids would see, you can, well, that the idea that voids expand more rapidly being close to Milne than a matter-dominated region. And so this bias is the whole analysis of the expansion of the universe.
I see. Okay, thanks. Do we have other questions?
Can I ask you a question?
Yes, sure.
Yeah. Hi, Lars. Thank you for the,
Yeah, hi.
the talk.
Yeah,
Hi.
nice to see you.
I have a question, sort of a matter of principle, if connected with the notion of a cosmological model. So we have to pick this time like GDC congruence in order to talk about the thing that's expanding.
Mhm.
It's not space-time, it's the congruence. And if you pick, for example, Milne, then you have a kind of model like an exploding bombshell and in flat space. But you neglect the matter. I mean, it's a vacuum solution. So
Yes.
I wouldn't trust that model at the vertex because there it's infinitely dense and
Of course, yes.
you just draw the lines, but there is nothing to look at to identify with the lines, because if there were matter identified with the lines, you should have included this in your equations. And so
yeah.
yeah, and I mean, this goes on. It's you can foliate say de Sitter in a positive curvature, zero curvature, negative curvature way, and so on. So what is the principle that we are lacking here that sets the choice of the congruence? Do you know what I mean?
Yeah. I don't have a ready answer to that. Of course. I mean, the universe is not perfectly empty. That's so. But also, I mean, but the whole notion that matter in the universe behaves like a fluid, I think it's not that takes some argument. I think that's one of the issues, right? So there is no, where do you find such a congruence? It's not obviously there.
Yes, exactly.
And I mean, Milne is actually Milne is actually a very interesting guy. He was actually thinking about, he came from sort of gas dynamics and stuff like that, right? And he wrote some very, very interesting things about, what, from his point of view, what potential sort of misinterpretations of the observation that matter is expanding, which I won't go into, but he is actually someone who should be at least read for enjoyment,
Okay.
So he also at some stage visited Germany, I think Berlin, and he felt kind of quite mistreated by Einstein.
Mm-hmm.
So there's some interesting quotes about that as well. But so I think his point of view, coming from gas dynamics, was basically that if you imagine yourself as sitting on a particle in a gas, you could come to the illusion that there has been an expansion.
Yes.
Yet you're basically in a homogeneous gas, but there's this kind of chaotic motion. So I can't really make justice, give justice to what he was saying, but he was quite a radical thinker, actually.
Mm-hmm. Thank you.
Do we have other questions?
Can I ask another question?
Yes, sure.
So, what's your take at the moment of this? I know that you've been working on this and this back reaction stuff and this original Ehlers-Buchert idea that sort of it's a sort of an inhomogeneity effect that we see an effective lambda. And since you also mentioned David Wiltshire, I mean, there are tons of papers about this. What's the present status of this?
Well, I mean, I have to say, I mean, so the Ehlers Buchert, that original paper was a Newtonian analysis.
Yes.
Then various people, including Thomas Buchert, have tried to argue about averaging and back reaction and so on. I personally, I don't think along those lines. I think it's very difficult to justify that point of view. Also George Ellis, many people, this whole fitting problem, all of that. Yeah, I think that's I think that should be basically avoided. Basically, I mean, I don't. There for sure there are dynamical effects coming from the fact that you have inhomogeneities in the universe, but you introduce a prejudice by talking about averaging and fitting
Yes.
and so on. I think that's something I want to avoid, basically.
So you would say it's inconclusive because there's so many different ways of doing it.
Yeah, and I mean also,
Then you can get
Bob
almost any
Wold
result.
had, he tried to argue the opposite,
Yeah, I
that
know.
that inhomogeneities can be neglected dynamically,
Yes.
and we wrote a paper, basically arguing against this. But I think I mean, seriously, the only way out is to do sufficiently large scale numerical studies, and I mean those are being done, but in basically using Newtonian physics. I mean those are very, very large scale, very expensive computations, these n-body simulations and all that. But it's not clear to me if they take into account general relativity in the proper way. So I think that's really a problem for the future. And it's almost, even like genes instability, things like that. There's the proper analysis and understanding of that, at least, on a mathematical basis, is limited, I would say.
Yes, thanks.
Okay. I would say we have time for one last question if someone has something urgent. If not, then let's thank Lars again. Thank you very much, Lars. It was a very nice, interesting talk.
Thank you.
And yeah, bye-bye, everyone. See you.
Okay.
Okay, bye-bye.